Okay, this is a follow-up video with question 38. So for question 38, although this thing looks like a loop of wire, it is actually a metal bar. Okay, so imagine that it is just one long straight metal bar. Okay, now the thing about this is that when the metal bar is moving through this uniform magnetic field, it is going to experience a rate of change in the magnetic field because it is moving, right? So because of this changing magnetic field that this bar is experiencing, is going to generate and induce EMF, and so there will be a current. Okay, and so if you look at the Lanz's law, you will also know that the direction of the current flow must oppose the direction of the oscillation. So now, this thing may confuse a lot of you because then you say that, okay, if it is a bar, that means it is like similar to a wire, it's going to produce a circular magnetic field. And this circular magnetic field is going to interact with this uniform magnetic field, and then it will be like, oh my god, how am I going to visualize the interaction between a circular magnetic field with a horizontal magnetic field? It's going to make your mind really confused. Now, if you look through your textbook, you will notice that actually your Fleming's left-hand rule is actually a shortcut, okay, to tell you, to describe to you the interaction between wire, the circular magnetic field, with a uniform magnetic field. For example, when you use your Fleming left-hand rule, let's say the typical question is that, okay, you have a wire, then you have these two magnet, okay, in between, and now you pass a current through. How will the wire move? Okay, if you look at this case, what this case is about is that when you have a current flowing through this wire, the current will generate a circular magnetic field, right? Yeah, and then this circular magnetic field is going to interact with the uniform magnetic field between this permanent magnet. And the interaction between these two magnetic fields will either cause the wire to go up or go down or go left or go right, right? And the textbook just tell you that, okay, in this case, you can use your Fleming left-hand rule to help you to visualize it. So when you have this kind of case, you say that, okay, the magnetic field of the north-south magnet will cause a magnetic field going this way, and now the current is going into the paper, so this way. The current is going into the paper, the field is this way, and so there will be a force going down, and so you know that, oh, okay, the wire is going to go down. So actually you have learned about the interaction of a circular magnetic field with a uniform magnetic field. Okay, and we have taught you to use your left hand to simplify this interaction and tell you directly how the force will go. So if you have this understanding, you can then attempt this question. Now, when you attempt this question, number one, you know that by Fleming left-hand rule, if your bar is swinging to the right, that means velocity is going to the right, then Lanz's law says that the current that is being induced will produce a force that is going to oppose this motion, right? So now we know that, okay, the force must be here. The force produced must be here. And my magnetic field is coming out of the paper, right? So the force must be here, magnetic field going out of the paper. So how will my current move? My current will, oops, sorry. My force is here. So my finger, this finger must be here, so I have to point towards the thing. So if that is the case, how will my current move? My current must go, and my current must go this way, must go down, right? Yeah, yeah, it will be here. Very hard to position with my handphone, with my video on top. So if you try to use your hand, you will notice that, okay, my force must be here. My magnetic field is going up to out of the paper, so my current must go down. So in this case, it means that the induced current, in order for the induced current to produce a force here in a magnetic field that is coming out, my current must go from P to Q. So with that understanding, you can now deduce the direction of the current is P to Q. And if you look at your option A, it says that the current flow from P to Q, okay, when your velocity is in this direction. Okay, then of course, if now your rod is here and the velocity is this way, when it swings back, the force must be here. So if the force is this way, it is from P to Q, and if it swings the other way, the force will be opposite, and therefore the current must reverse from Q to P. Okay, and it is because the force produced must oppose the direction of the oscillation. Okay. If you cannot position your hand for the Fleming left hand rule, do come and look for me. Your hand should look something like that. Okay, for this swing, the swing to the right. So when you swing to the right, the force will be towards the left, and this finger, the magnetic field, will be always pointing up. So if you orientate your left hand correctly, the current will point down. And if you do it the other way, that means when the swing is this way, your hand will go somewhere like that, because the force is now towards the right. Magnetic field is still pointing out, so your current will be going from Q to P. Okay.